Top of the morning.
Welcome everybody to the first episode of Table Talk, where we talk about fascinating physical phenomena.
Cheers. Coffee.
This episode, Kyle and myself will talk to you about anyons. Kyle, what's an anyon?
Let me tell you, Ben. Excuse me. An anyon is a quasi-particle. So a quasi-particle can be defined as something that has momentum and position in space. Examples of this that we would understand would be, say, phonons or holes. So a phonon, a sound wave traveling through a lattice. If we pick a point, that point has momentum associated with it, and we can almost treat it like there is a particle there, when in reality there's not. Another example are holes. If we have conduction going on, there's a hole, an electron comes and fills it, but then there's another hole over here, electron comes and fills it. And we can model this as essentially the hole moving, when in reality there's not actually a particle there, but there are particle-like excitations. And that is essentially what a quasi-particle is.
Fantastic. In the world as we relate to it, 3 dimensions, particles are classified as either fermions or bosons. These particles follow Fermi-Dirac or Bose-Einstein statistics. However, in 2 dimensions we see the emergence of anyons. And these anyons follow something known as braiding or Annie statistics. So for a moment, let's consider a system of 2 identical particles. So we have 2 particles, one in position 1, one in position 2, and then we will swap them. When we perform this swap with fermions and bosons, we see the emergence of a plus or minus 1 phase factor. Plus 1 for boson, minus 1 for fermion. However, in 2 dimensions, when working with anyons, and we have a system of 2 identical anyons, and we swap them, this emerging phase factor is actually e to the I theta, where theta can range from effectively 0 to 2 pi. And as we let it be 0 or 2 pi, we get the familiar boson plus 1, and as we let it be pi, we see the familiar negative 1 for fermions. However, it can range in between them as well. Which is pretty bizarre.
It's pretty bizarre.
Yeah, I'd agree. So, where might we observe these things? Well, a very significant experimental setup, known as the fractional quantum Hall effect, these anyons can actually be observed. So, what is the setup? We'll take a 2-dimensional electron gas, and we'll sandwich that between 2 semi-conducting plates. We'll then bring that setup to a low temperature, and apply a strong uniform magnetic field through the plane. In these conditions, we can see electrons actually begin to fracture into any odd integer number of particles. However, for this example, we'll say it fractures into 3. Each of these particles will then carry a 1/3 of the electron charge. And these particles are said to be in an FQH, or fractional quantum Hall state. These particles are also known as anyons. Anyons can then be further classified into 2 different classifications, known as abelian and non-abelian. Abelian anyons are great because they have been experimentally observed. However, only properties that are theoretically predicted to be non-abelian have been observed. So the non-abelian anyons themselves have not been observed. So to understand the difference between these 2 things, we're going to have to be introduced to the idea of braiding.
Are you talking about braiding my hair?
No, Kyle.
You don't want to braid this lock?
We can do that later.
Okay.
Anyways,
braiding. So what the heck is braiding? Let's draw a picture. So braiding is essentially taking 2 particles and swapping their positions, or braiding their world lines. It's really easy to see if we draw a picture where our y-axis is time, our x-axis is just the position of 2 particles in space. So if I take these particles and I swap their positions like this, we have a braid. All I've done is taken the particles and I've switched their positions. And this can be done for multiple particles as well. So if we draw the same thing, same setup, but this time we have, let's say, 4 particles. And let's consider all these particles to be identical anyons. I can do the same thing. I can take these particles and I can swap them and cross their world lines. Let's say I do that, and then I swap these two particles. And then lastly, let's say I take these two particles and I swap them up here. As you can see, I've taken these 4 particles and I've intertwined and switched the positions multiple times, giving rise to 3 different braids in here. And so the difference between abelian and non-abelian anyons comes down to the order at which the particles are swapped in time. So let's say this is swap 1, this is swap 2, and swap 3. So for abelian anyons, swap 1 and swap 2, the order at which they're done comparative to the initial and final doesn't matter. So 1 times 2 is the same as 2 times 1. So those swaps, the order doesn't matter. But for non-abelian, the order of these swaps does matter. And it plays a crucial role. So swap 1 multiplied by swap 2 is not the same as swap 2 multiplied by swap 1. And it's a very interesting property about non-abelian anyons, because that swap order, every time that we swap 2 particles, a phase factor is introduced. The phase factor that Ben was talking about, the e to the I theta, is introduced. And so every time we do a swap, we introduce a phase factor. And yeah, that is the difference between the abelian and non-abelian anyons. So, why does this matter? Why are we interested in anyons, especially if we haven't even experimentally seen some of them? Does Anyon care?
Well, as it turns out, people actually do care about this. Specifically, people involved with quantum computing. They have a strong interest in specifically non-abelian anyons due to the fact that on their due to the unique output of their swaps. So if we can control these swaps, we can then encode information in the system. Thus, we can do computation.
To further illustrate this point, we'll show you a quick video so you can understand kind of what that looks like a bit better.
Okay, so now let's talk about quantum information. So, the usual problem with why quantum computing has proven to be so hard is that basically external noise from the environment is always sort of corrupting the quantum information which we're trying to so desperately to preserve in our quantum computer. So for example, a stray bit of photons might leak into the quantum computer. And if you're trying to store the quantum information in some local property of your system, maybe a property of an atom or something like that, well, that photon can hit the atom and then mess up your quantum information. However, these bubbles that carry fractional charge, which we were telling you about, they're called anyons. The beautiful thing about this is that you can use their behavior to make a noise-free quantum computer.
And we're back. So as you saw in that video, the non-abelian anyons can be used to encode information and keep that information safe from corruption. If we were to use other particles like electrons or protons, that information that's encoded is much more susceptible to corruption compared to these non-abelian anyons. They're much more safe from corruption because of their 2D braiding that cannot be undone in 2 dimensions, allows us to encode information and memory much better without corruption.
Yeah, however, as we mentioned earlier, non-abelian anyons are still a thing of theory, which means a significant amount of, improvement in the field is required before this can actually be a thing that we can use. So yeah.
Yeah, if you want to research that field, go for it. Quantum computing is a very interesting field. If you want to know more, look into some other videos. But as for this video, that was Anyons. Hope you enjoyed it. Hit subscribe.
Come back next time.
Drop us a like. Comment. I'm not saying